Hi everyone, my name's Lien and I will be talking the section on microfluidics and soft-lithography this afternoon. Just before we start, can I just get a show of hand who has worked with or heard about microfluidics and soft-lithography? Okay, a few there, that's great. Alright, so this is an overview of what we'll be covering this afternoon. So initially, we'll talk about microfluidics, and then we move on to soft-lithography. So under microfluidics, we'll go into an intro of what it is, the basic fluid mechanics that's involved, the type of materials and fabrication process that you'll encounter if you're dealing with microfluidics. On the soft-lithography side, we'll again introduce what soft-lithography is for those who haven't worked with it before. We'll look at the process, the material that's used, mainly the PDMS, surface treatment, and also the characteristics of PDMS and ways to go around with the issues with it. Then we'll look at just a very typical experimental setup and the issues with air bubbles that most microfluidics people will encounter. So moving on. So what is microfluidics? It's essentially the control and manipulation of fluids at a micron scale. So you think about rivers, fluids flowing, and you actually then bring that down into a microchannel, so basically the size of your hair. Bringing a macro scale down to a micro scale, you actually will see different phenomenon as opposed to when you're looking at fluidics at a macro scale. So the advantages of bringing a large volume down to a small volume includes the reduction of reagent costs. So if you're running PCR, for example, the reagents can actually be very costly. So reducing that volume down to, say, a few microliter, that will drastically reduce cost. It also increases the speed of reaction because you're basically putting the fluids at a shorter distance, so they'll see each other at a shorter distance faster. And also with the small volume, you get safety factor as well. The other advantages of using a microfluidic device is that there's lower power consumption, and you can also bring in many aspects onto a chip and create a lab on a chip. So basically doing a lot of things in the lab, but on just a chip that's portable. It's also ease of disposing of device and fluids, so it's just a chip that you can just throw out, whereas if you're dealing with large volumes of certain hazardous solution, then you'll look at the safety, OHS, and all of that. With microfluidics, you'll also be working with high surface to volume ratios. So you'll be looking at laminar flows. So I'll be talking more about that in the next couple of slides. And just recap on that aspects of microfluidics being a small size is actually quite portable. So if you it's great for diagnostic devices, for example, and you can bring it out onto the field, do a rapid test and so forth, rather than a huge setup of labs. So types of flow in microfluidics is mainly dominated by the laminar flow. So if anyone here who has done fluidic or fluid mechanics would have encountered the Reynolds number. So Reynolds number is a dimensionless number. It's a measure of turbulence, and it's basically looking at inertia versus viscosity. So with the microfluidic devices, normally the Reynolds number is less than 1, so it's a really small number. And in those cases, viscosity actually dominates the system. And in most macro scale, most of the fluid flows, like rivers, streams, and so forth, is actually quite turbulent. So laminar is the main thing in microfluidics. So viscosity is a very important parameter of a liquid that you would look at when you're dealing with microfluidics. It's basically the measure of how the fluid flows. So the classic examples is water versus honey. So water you can actually pour quite easily, With honey, you probably take a bit more time. So honey is more viscous than water. So bringing viscosity into the types of fluids, there's mainly two types of fluids out there. You either have Newtonian fluids or non-Newtonian fluids. So Newtonian fluids follow the Newtonian's law of viscosity. So that's where there's linear relationship between the stress and the strain. So for example, fluids that's flowing, so there's two plates here, and if the top plate's moving, it actually causes a shear in this direction. And with that velocity, you can actually work out the shear rate. So shear rate is this gradient here. So in Newtonian fluids, the viscosity actually remains constant, okay? Whereas non-Newtonian fluids is obviously changing with the shear rate. In microfluidics, mostly we deal with Newtonian fluids. So it's in rare cases that you deal with non-Newtonian fluids. And one of the rare cases I can think of is if you're dealing with blood. So if anyone doing diagnostic tools dealing with blood, then maybe that's a special case where you have to look more deeper than just using the Newtonian fluids case. The other key aspects in microfluidics is surface tension. So surface tension is, when you're looking at the droplets, it's how it holds the droplets in place. And basically, we look at the molecules within that droplet. These molecules here has a higher adhesion force towards each other. And these molecules at the surface, having less neighbor to see, it actually pulls more strongly towards the bulk particles there. So what it creates is basically the surface tension here, and basically you can see like a film. And it's also the reason why a water strider can actually float on the film of the water. Now, its surface tension is absolutely critical in microfluidics, and that's due to the large surface to volume ratio that we normally deal with in microfluidics. So another aspect of surface tension that we need to look at is contact angle. So contact angle is dealing with how the interfaces see each other, and the contact angle is the angle at which you take a tangent line from the point that the three phases see each other, and that there is the contact angle. It's actually a measure of wettability, so how hydrophobic or hydrophilic a surface is. So in this case here, hydrophobic is where the liquid actually has a contact angle of less than 90 degrees, and where the contact angle is larger than 90 degrees and up to 180 degrees, it's termed as hydrophobic. So hydrophilic and hydrophobic. So here is the Young's equation that many may encounter when they're dealing with surface tension. And it's basically taking into account all the surface energy or interfacial tensions of these surfaces, and then calculating the surface, the contact angle from there. So knowing surface contact and the contact angle, so what's from there? So one of the equation from Young-Laplace, which actually looks at the pressure within a drop of liquid at the air and liquid interface. So basically, it's the pressure inside versus the pressure that it sees outside. And for simplicity, we just look at a spherical droplet, and that would just reduce the equation down to the pressure drop times the 2, and that's the surface tension over the radius of the droplet. Now, if we compare two droplets of different radius, so if you look at this, if you have a small droplet versus a big droplet, with a small radius, the pressure drop internally for that, the pressure drop for that droplet is actually higher than if you have a big radius. So when you're connecting a small droplet to a big droplet, what you get is the small droplet will flow towards the big droplet because it has a higher pressure, internal pressure than the bigger radius. And so it's quite useful in microfluidics because you can connect the two droplets via a channel and you get the drawing effect where the flow is going from the small droplet to the big droplet. So in effect, you're creating a passive pumping system. Now, this is passive in the sense that you don't have any mechanism on top of that. The normal way that we run with microfluidics is that we actually have a syringe pump. So comparing the passive pump system here to a syringe pump system, which is where you actually need a physical syringe pump, the advantages in this case is that it actually can go down to a lower flow rates as opposed to a syringe pump, because syringe pump is mechanical, and sometimes you also get this instability when you get into down of a low flow rates. So basically, when we work with microfluidics, we also look at capillary. So capillary is where the fluid is drawn into a channel, into a small channel, and that's on the condition that if this surface has a higher adhesion forces, or for example, if we're looking at water, if this surface is hydrophilic, then this surface will cause the surface tension and also will be pulling the flow that direction. So it's highly useful in microfluidics, especially if you just want to flow it without any means of, say, a pump. Here is a capillary pressure drop equation. You can actually use that in hand to work out the flow in this channel here. And here I actually put in two equations, one for the rectangular duct and one for the circular pipe. And the reason for that is that normally people start off with the circular pipe deriving of equations, but in microfluidics, because of the fabrication process, most of the channels are not circular. Most of the channels are rectangular or square. So in that case, here is just an equivalent equation to use for a rectangular channel. So one good example of how this is actually used in real life is a blood glucose monitoring strips, where a droplet of blood can actually be drawn into the strip, and it reacts to certain actives on the strip here that it actually gets some reading onto the monitoring system there. So I won't carry too much on to details about these capillary effects, but this is just some of the other examples of capillary effects that you can actually look at when dealing with microfluidics. There's passive capillary effect, which is actually similar to what we've been talking about before. It's looking at the geometry of the channel and using the surface's wettability and gradients to drive the liquid. Another one that for electronics and so forth that you want to look into is called the electrocapillary effect for electro wetting. That's where charges are made across the between the liquid and also the plates that's seeing, so then you can drive it with the charges. The changes in potential difference. And then the third one is thermal. So you can actually use temperature to drive the liquid and control it. So at high temperature, usually liquid molecules moves faster, and then causing it to have a lower viscosity and lower surface tension. This is just an example of how the capillary and also the surface treatments and so forth is used in microfluidics. So this device here is a blood and plasma separation device, and basically the key point is here. So the researchers here actually used oxygen plasma to treat both ends of this cylinder here, so that the ends here are hydrophilic, whereas in the center is hydrophobic. So it creates sort of like a jump barrier for the blood to go through. And what happens is at that region there, the cells, because it's heavier, it actually slows down and creates a somewhat they call self-built-in filter. and then the plasma can still then continue on to go across. So it's quite a nice experiment where they are able to separate the cells versus the plasma part of the blood. So another key aspect of microfluidics is diffusion. And diffusion is basically the transportation of a particle from higher region of concentration to a region of lower concentration. And here is the Einstein-Stokes equation for the diffusion coefficient. And here is another equation that's quite nice to use, is where you can actually determine the time from which the particle can actually travel across a width W there. Now, I put an example of hemoglobin there. And what I want to demonstrate here is why diffusion is so important for microfluidics. Because if you compare microfluidics at 10 micron width, as opposed to a macro scale of 1 centimeter, the hemoglobin to travel 10 micron, it needs 1 second. Whereas if the channel is 1 centimeter wide, it takes about 10 to the power of 6 seconds. So it takes too long to move across that channel. So in a small channel with a small time frame, that's why diffusion is actually so important in microfluidics. So here we're still on diffusion, but instead of just looking at a one direction flow, we can look at also the distance at which the length of channel at which it requires for full diffusion of the particles. And down here is the Peclet number, and its definition there is the number of channel widths required for complete mixing. So what we can do is now look at an example of a small protein, their size 5 nanometer, with the diffusion really, which is the key, is 40 micron square per second. So if we're looking at that small protein for a 100 micron channel width and for a 100 micron per second velocity, you can then get a Peclet number of 250, which is like 250 channel widths in order for the complete mixing to occur. And if you're taking that into account, you then can actually work out the distance, the length at which the channel is required for that complete mixing, and also the time. So it's quite nice there for working out diffusion. Diffusion is significant in microfluidics, but sometimes it can be quite slow. So there are methods that's out there to hasten that process a bit or to encourage more mixing. And one of the study here is to incorporate grooves and valleys into it to basically bring the solutions together even further. And this here is called the herringbone structure. Over here is another type of micro mixer, and it's three-dimensional with serpentine weaving of channels to create that mixing effect. So it really depends on what the system you're after, whether you want slow diffusion or fast diffusion. There are ways to go around that. So droplet formation is another interesting aspect of microfluidics. So far in the diffusion regime before, we were talking about the fluids are miscible, meaning they were flowing together in one stream, down in one direction. But in cases where the fluids are immiscible, you can actually create droplets. And here are 3 classical examples of methods or designs to create droplets. There's a T-junction, flow focusing, and co-flowing systems. So in these systems here, there are competing stresses. So basically, there's competition between the surface tension and the viscous stress. And that can actually correlate down to into an equation like this, and you can actually get a characteristic drop size. And I just want to emphasize that this is actually an estimate. Everything comes down to when you fabricate and run the experiments that you can actually then get the actual dimension of the droplets. Here is a study of a flow focusing setup. So this diagram here is just showing the flow regime where the researcher actually just put the flow of oil. So this is an oil and oil and water system. So out here is oil, and that's the water in there. So it's comparing the oil versus the ratio of oil to water ratios. So it's just a regime of the flow and the types of droplets that's generated in the experiments. Now, the common issues with droplet formation, there are two main issues, and these coalescence, where the droplet downstreams actually sees each other, and then they form together. They break the surface tension, and then they just come into be one big blob, say. And there's wetting. So wetting is an issue where in multi-phase system where you have hydrophobic and hydrophilic liquids, and if you don't treat the surface properly enough, what happens if you have a hydrophilic solution that sees a hydrophilic surface, and it will just starts to wet that surface there, and it would not allow droplet formation to occur. So there are possible solutions to that. You can actually use surfactant, which I'll explain a bit further in the next slide, or you can actually chemically treat the surfaces to have certain areas to be hydrophobic and certain areas to be hydrophilic as required for the system. So for example, you're flowing fluid in there, you want those sides there to be hydrophilic, and then you treat these surfaces out here to be hydrophobic. So surfactant. Surfactant is very useful in microfluidics, especially for droplet formation. It's a surface agent, surface active agent, and what it does, it lowers the surface interfacial tension. And one example is detergent. So detergent actually you use to wash your hands that breaks up oils and so forth. And this is just a typical structure of a surfactant. It has a hydrophilic head and a hydrophobic tail. So it has the characteristics of hydrophobic and hydrophilic. And in this system here, where you have water, cell media, and proteins per se, that's flowing into oil, within that regime, within that system there, if you have surfactant, what happens initially is the surfactant will come to the surface, see the blob of the droplet of water there, and the head that's hydrophilic will be heading in, and then it will create, and the hydrophobic tails out. And what it does is over time it creates a barrier around that droplets there. So it creates it stabilizes the emulsion. And it also then, if you have any cells or biomolecules in there, it actually prevents them from attaching to the surface of the droplet, so further stabilizing the system. Now, the surfactant can actually be designed, or you can actually choose it off the shelf. So here are the key things to be mindful of when selecting these surfactants. So mobility. So you would like the surfactant to reach the surface as soon as possible, because there's no point of having surfactant seeing the droplet and working and being active downstream when perhaps it might already coalesce and so forth. So you want the surface surfactant to be active, to be working and reaching the droplets as fast as possible. So that mobility actually depends on the size of the surfactant and also the properties of that surfactant. So in general, you would probably, if you wouldn't want to have too large of a molecular weight surfactant, because then it will take time for it to travel to the surface. The other factor that you want to keep in mind is the critical micelle concentration. So critical micelle concentration is where the concentration where the surfactant comes together and see itself, and then forms a sort of like a bore, a sphere. So in that case, it's actually taking up the concentration of the leftover surfactant for it to act onto the system. So you would want to choose a concentration of surfactant that's below the concentration of the micelle concentration. Otherwise, it won't be as effective. So flow in channel. Now we're moving on to what if there is fluid flowing in the channel? What do you need to look out for? So in the design of a microfluidics, before you start off running experiments and so forth, it's probably worthwhile to take a look at the entrance length. Now the entrance length is basically the length in which it takes for the fluid to stabilize and create a parabolic flow, or a fully developed flow. Because at this stage it can be chaotic, it can be changing, it can be unstable. And that might interfere with your experiments. Now, if your device or channel length is about 70 times more than the diameter of the channel that you're working with, then probably you're on the safe side and you don't need to worry about it, and just worry about dealing with the length of channel after that 70 times factor. However, if your device for some reason needs to work in a very short distance, and then any entrance or rapid change or entrance into a turn become significant. So that's where you would probably want to work out what the entrance length is. Here is just an example of a study for these conditions, that you can actually use these constants to work out the entrance length. So the flow in microchannel is on the condition that it's laminar, Newtonian fluids, incompressible. Then you can actually use this generalized Hagen Poiseuille flow, and this is the equation for it. So basically, it allows you to work out the flow rate, the resistance, the dimensions. It also relates the dimensions to the pressure drop. So here I've included just two equations that might be useful. So normally, again, like I said, people characterize flow with a circular cross-section. But in reality, when you're dealing with microfluidics in the fabrication process, you'd probably be looking at rectangular channels. So here, depending on the aspect ratio of your channel, you can use this equation when there's low aspect ratio. And for higher aspect ratio, you can use the resistance there. So just basically plug the resistance back into this or into here, and you can work out the flow and the pressure drop. So some people would come to me and say, how do you start off designing a device or a microfluidic network or a device? So I'll probably say the easy way to do it is probably consider fluids as circuits. So, for example, here it's a microfluidic network, and here's the electric circuit. So the analogy is represented in this table here. So volumetric flow rate is equivalent to the electric current in an electric system. Pressure drop is equivalent to the voltage drop. Hydraulic resistance is equivalent to electric resistance. And here is probably where I would say most useful. The equations that relates the parameters to one another, and the analogy to the electrical circuits. So if we just record the Hagen-Poiseuille flow law that we just mentioned previously, that is equivalent to Ohm's law. And then you have the law of mass conservation, which is equivalent to Kirchhoff's current law. And the law of energy conservation is equivalent to Kirchhoff's voltage law. So if you look into details, the law of mass conservation here, it's basically the sum of flow rate into a node is 0. So this here is a node. This here is a node. So if we look at this node here, the sum of flow rate into that node is 0. So basically, this flow rate minus this flow rate minus this flow rate minus this flow rate should be 0. So over this node here, the sum of this flow rate plus this flow rate plus this flow rate minus this flow rate should be 0. And then the law of energy conservation. So the pressure drop, or the sum of the pressure drop, is zero in a closed path. So if we say we look at this path here, that's closed. So the pressure drop here minus the pressure drop here should be zero. Okay? So keeping those in mind, that will actually give us some equations to balance out. So this is an example of how the calculations or the equations before is implemented from a design and then into a microfluidic device there. So you can set the conditions, and also you can set certain channel dimensions, and from there you can work out. Now, then people will probably say there's also software out there that can actually do these generations for me. Then why am I having to calculate all this out? Well, then you have to look at what software that is, and also the computer power that's required to generate and simulate certain flows. So this is probably just a nice, quick, sit down, draw out, rather than sitting down with a powerful PC that probably requires a bit of time to run as well. Here we're just briefly looking at the types of materials used in microfluidics. As you can see, there's plenty of different types there, from elastomer, PDMS, to plastics, to thermal set polyester, silicon and glass, paper-based, hydrogel, and also then hybrids of these. Now, silicon and glass and probably PDMS are probably mostly encountered. Elastomer PDMS is probably the most used because it's so cheap and easy and fast. And the silicon glass wafer is actually more expensive to fabricate, even though it has a desirable characteristics where it's hydrophilic. So elastomer is hydrophobic, and this is hydrophilic. The other materials also have their own drawbacks. So hydrogel can actually be quite soft, and depending on the system that you need, sometimes you need it for it to be more robust and so forth. So these plastic here were 3D printed. So 3D printer has now become a more used equipment in microfluidics fabrication, which I'll talk a bit more later. But probably the limiting factor at the moment for 3D printers is just the resolution, how far down it can actually go. So yeah, it depends on the actual 3D printer you're looking at. You can get down further, it's just the price of the machine might be a bit hefty. This is just a table showing some of the properties of the materials that we just looked at. I'll probably focus more on the elastomer at this stage because for the next talk we'll be on soft-lithography, and that is the key material in the process. But basically it's easy to use, and you can actually generate 3D structures with it. It's soft though, so it's a low young modulus material. And the drawback, probably hydrophobic, but I'll talk more about the surface treatments that you can do on the PDMS to change that. So the fabrication of microfluidics, this is just a nice flow that from a paper I took out, and the reference down here, is looking at how the materials is then go into fabrication, and also just how it's all relate to each other. At the moment, for most of the process at our facility, we go from PDMS to microfabrication, and then to the PDMS casting, and then to the oxygen plasma for bonding. So that's probably the main route that we're taking at the moment. Obviously, there's other options out there. The CNC machining, laser machining, digital craft cutter, and also there's the 3D printing, which I just mentioned before. There's also hot embossing, inject molding, and roll-in printing. Now, I just want to flag out there that we do have hot embossing at our facility, so we can actually hot emboss fluidic devices. However, there's also drawbacks with that in terms of the material of choice being plastic, and it can be actually slightly more expensive than PDMS. This one, I thought it's nice to put in there in terms of the volume output and the PDMS where it lies in terms of, if you want, PDMS is only used for mostly at the research level, but if you want like industry and level of bulk fabrication, then you probably want to go more like thermal injection molding and so forth. So this is just to see where PDMS lies. So what is soft-lithography? Soft-lithography is the replication of the patterned structure from a master onto using soft elastomer. The advantages is that it's rapid, simple, and inexpensive. You require a mold though, and you also require the elastomer. And the feature can go from microns to nanoscale, and this actually depends on the environment and also on the mold that you have. So if you have a mold that is EBL generated with nano features, you probably can cast it off. But yeah, it depends on what type of molds that you have. Most of the mold that we use is actually SU8 mold, which fabricated from the photolithography process mentioned previously. So this is the photolithography process pretty much mentioned before. So with the soft lithography, we just cast the PDMS onto the surface by mixing a polymer with a cross-linking agent. And then we basically cure it, and then you can peel it out and it becomes the mold. Then you can actually punch holes and bond it together. Okay, so that's just a very quick flow of the soft lithography. So PDMS is the key material used, and the reason why it's widely used in microfluidics is because it's inexpensive, it's transparent, it's non-toxic, and it's actually hydrophobic, but you can actually make it hydrophilic upon surface treatment. And these are all the other characteristics, as well as some non-polar organic solvents. And it actually is permeable to gas. Maybe that's a favorable characteristic you want. And it's soft. So some of the key surface treatments that carried out in PDMS, one of them, the main thing is oxygen plasma. So you basically put the hydrophobic PDMS into oxygen plasma, and there it generates a silanal surface for then to react with other surfaces like other PDMS or glass, silicon, and also some plastics. So this bond here is ideal if you put the surfaces together within, say, the first 10 minutes after plasma treating, because after that time, what happens is that the surface here actually reverts back to its original structure. So this is not permanent at this stage here. However, the bond itself, once you put something on top, within that 10 minutes after plasma treatment, is permanent. And the bond can be quite high, and it can withstand pressure up to 30 to 50 psi. So cyanidization is another surface treatment involved, and basically it's treating the master after fabrication so that it prevents the PDMS from sticking to the surface. And here, normally they use, under vacuum, they use a fluorinated silane agent to deposit that non-stick layer onto the wafer. So it's necessary if you have features that's less than 20 micron or high density, and especially if you have high aspect ratios like tall pillars or deep wells, then you definitely need it. You might be able to get away with not treating the surface if your device design is really big, like say 50 micron upwards. So some of the drawbacks of PDMS is that it's soft. So with soft, you can get deformations of PDMS, and it also limits the aspect ratio of which you can actually make your structures. Now, there's ways you can go around that. You can either reduce your aspect ratio down, or you can actually tune the PDMS. So the PDMS polymer to cross-linker ratio can be tuned to make it a bit stiffer. So that might be a solution to that problem there. PDMS actually shrinks after baking, so the rate of shrinkage is roughly about 1%. Maybe it's not a big deal in your device, but maybe it is, depending on your device dimensions. So the way to go around it is actually to take into account that percentage of shrinkage when you're designing your device. And when you're fabricating, especially for multi-layers, it's best that you actually do the device and bonding in the shortest time period to eliminate any discrepancy between the layers due to shrinkage. So this is a typical setup of a microfluidic experiment. You have the pump, you have your device in there, you have it set up on a microscope so that you can actually track the flow and the image of the cell and so forth. Obviously, you also have the PC to capture that, data. Air bubbles. So whoever worked with microfluidics would know what I'm talking about now. It's nightmares in microfluidics, so air bubbles always an issue. And the reason why is that it can actually cause flow instability. It can actually constrict the channel and create increase in resistance. And it also can damage your cell culture if you have cells in there, so the bubble can just float across and scrape your cell layer. It also allows aggregation at the interfaces, and depending on what you functionalize your device with, the bubbles can actually damage your functionalized wall. It may be originate from many places, but here are some tips to search for where it comes from and to solve it. It can be at the start of the experiment when you set up, you actually have some air bubble gap in your syringe, so you just need to remove that air bubble as much as possible. Fluid switching, so whenever you switching fluid between experiments, you can always generate bubbles at that stage. PDMS is actually porous, so it actually can, depending on the gas flow and so forth, it can actually generate gas within the system itself. Leakage, so any leakage can be introduction of air bubbles. And also if there's dissolved gas in the solution, and when you heat it up, you can actually create air bubbles. So tips for removal of air bubbles, because I've been working with microfluidics for a while, and it's a nightmare. So tips to remove the air bubbles is to actually look at the design to avoid acute angles in your design. So that's where bubbles can be captured. Fittings, so make sure there's no leakage in the fittings. And if possible and appropriate, you can degas the liquids to minimize the generation of air bubbles. And also during fluid switching, so make sure you can remove as much air bubbles in the syringe and pipes and so forth, in tubing and so forth, before you reconnect them. And in some ways, you can actually create pulse or pressure just slightly to move that pressure, the air bubble along, and then you can actually remove it on the other side. Now that depending on your system, if you have cells in there, obviously you don't want to put more pressure in there, that might not be a good idea. Bubbles dissolution, so if you have pressure on both ends, you can actually force the bubbles to redissolve into the liquid. That might be one way to remove it. You can use soft surfactant or incorporate a bubble trap, so you can have like the tube running into a separate chamber, and then that chamber can then have a tube that links from the bottom of the liquid to eliminate the air bubbles there. And obviously, if you can, just use non-permeable tubing. That also reduces the chance of air bubbles in your system. And here is some nice work done by some researchers. I will briefly go through this. It's a self-powered microfluidic device, and it's a PCR device that actually has a self-built-in vacuum pump. So it sucks the fluid in by itself. And it goes through these reaction chambers to then get your reading out for the device. This is another neat device. It's a wearable microfluidic device made from PDMS, and it actually captures the sweat, and then you can actually look at the pH, the glucose levels, and so forth. So it's quite a neat device there. And here is a tree on a chip that's created by MIT recently. It's looking at passive hydraulic power that can actually, like a tree, mimic the trees and then create the fluid pumps around that. So that's the end of my presentation. Thank you. Any questions?